Hi, this video lecture is over sections 2.6 and 2.7 in the text. Before we get going, here are a couple of things you may or may not want to access. On Brightspace here in the example datasets folder, section 267 is the PDF of the document that I'm working on, so you can print that out and follow along as you wish. And you may not have access to SPSS right now, but for reference, the data file that I'll be using is here. So first, section 2.6 is on a topic that I'll call two-way tables. It is a technique that can be useful for analyzing paired categorical data. So for example, suppose we want to know the acceptance rate of applicants to a college differs by the gender of the applicant. So we get 800 people who applied, and we record their gender and admission status. These are paired data, of course. Both variables are categorical rather than quantitative, so it doesn't make sense to talk about correlation as we've been discussing. What we can do is tabulate. And so a female was admitted. I come to the female admitted cell and tally. Female was denied admittance, tally. Male was denied admittance, tally, and so on. When I get done, here are the counts in each entry of the table. And by the way, there's no reason that the number of categories in a given variable would have to just be 2. This is a 2 by 2 table, but we could have a 2 by 3 or a 7 by 4 or whatever. The next thing we might want to do is to compute percentages, and we can do that in either of two ways. One is we can think of the table by rows, and so in the first row among the male applicants there were 600 total. 200 total female applicants, and then I can compute 480 out of 600 is 80%, whereas 120 out of 600 is 20%, and so on. Or I could think of columns as the units, and there were 660 students admitted, 480 of which were male, so 72.7% of the admitted students were male, and so on. So what is the story coming out of these? Both of these two tables really give the same message. Here we might directly translate this into English as a higher percentage of the female applicants were admitted than of the male applicants. You can see that here, 80% versus 90%. Over here, I might say something like the percentage of females was higher among the accepted students than those denied admission. And I can see that here among the admitted students or accepted students, 27% were female, whereas in the students denied admission, only 14% were female. In either case, the conclusion here seems to be that females are being admitted at a higher rate than male students. Let's go to another example. Here, the data from survival rates 6 weeks after surgery is recorded from 2 hospitals. So the data look like this now. There are 3 variables. First of all, a measure of condition at the time of the surgery. So very crudely, the patients were classified into either good condition or poor condition. Then, in which hospital was the surgery done? And then after 6 weeks, did the patient survive or pass away? So there are 3 variables. I might now think about a 3-way table instead of a 2-way table, but that's hard to visualize. And when I get to a 4-way table, it's impossible to visualize. So then we start breaking things down in this kind of structure. So maybe I think first of all about a good classification and a poor classification. And then within those 2 categories, I can make a 2-way table of hospital versus survival status. So how would I do that on SPSS? If I go to the data file I mentioned on Brightspace, what I see is the following. Now, notice you might have been expecting to see hundreds and hundreds of these individual patients. What has happened is that some pre-processing has already been done. Some tabulation has already been done. So of the patients in good condition upon admittance who went to hospital A for surgery and then passed away, there were 6 of those, and good condition hospital B passed away 8 of those, and so on like this. And so this is not the raw data. These are labels indicating or corresponding to these counts. That's sometimes, but not always, how you encounter such data. So first of all, I need to tell SPSS that these are actual counts or frequencies when it goes to do calculations. To do that, I'm going to go into data and weight cases. The default is that SPSS should not weight cases, but if I check that I want it to, then it's going to ask me which variable to weight cases by. In this case, since count was the only quantitative variable, it already proposed that. And so I'll check OK. And now SPSS knows that the column count should be interpreted in a special way, that it controls or describes how many each of these rows really existed in the raw data set. Then we'll go to Analyze Descriptive Statistics and Crosstabs. Analyze Descriptive Statistics, Crosstabs brings up a screen like this. Now, if I remember how I wanted my table to end up looking, the big categorization was good versus poor, and then the hospital was controlling the column and the survival status, the row. So if I go here for the row, I will choose the survival status. For the column, I will choose the hospital. And then for something that SPSS calls layers, I'm going to choose the condition. In another data set, I might even have more variables, and so I can start creating more layers with this next variable if in another situation. Let's also ask SPSS to compute some percentages. So if I go here to cells, it's already going to give me the counts, but let's make it also give column percentages by checking this box. And I will continue and click OK, and I get this table. So now let me go to the handout sheet where I have that copied, and we'll talk about it. So the table is arranged a little differently than on my handout here at the top. in that SPSS put the good and poor categories horizontally like this. So I'm thinking about the table then as here's a block and here's a block. And then it went ahead and did totals as well. So these two top blocks are contributing to the bottom. Then, as we said, the hospital is delineated by column, and then survival status, dead or survived, in the rows. So let's ask a series of questions here now. Which hospital appears safer, that is, a higher survival rate for patients in good condition? Okay, good condition. I'm interested in survival status. And so this is the row of the table that I'm interested in. And if I take a look at what it's saying in hospital A, 99% survived, in hospital B, 98.7% survived. And so hospital A has the higher survival rate for patients in good condition. What about in poor condition? So now I come here. And I see that hospital A has a slightly higher percentage as well. So then total is just these two results put together. And I come here and I actually see that B has a higher overall survival rate. So now I have this weird situation. If you're in good condition, you better go to hospital A because it has a higher survival rate. If you're in poor condition, you better go to hospital A because it has a higher survival rate. But if you don't know your status, then maybe you're better off going to hospital B because it has the higher survival rate. This is a paradox, right? How can A be better at treating patients in both good and poor conditions, and yet B is better overall? So this is an example of something called Simpson's paradox, and it comes up in real life examples in the news media quite a bit, actually. So if you think carefully about it, notice some key facts right here that if I look at the number of patients in good condition, 600 of them went to A, 600 of them went to B. The good condition patients split between the hospitals. But if I look at the patients in poor condition, 1,500 of them went to hospital A and only 200 to hospital B. So you might think about A as being a regional hospital and B a small town local hospital, for example. And in that situation, maybe the patients in good condition would split equally, but patients in poor condition might be sent to the larger hospital to begin with. And so hospital A just ends up with a sicker sample overall. And therefore, even if their care is overall better, their survival rate is lower because of the proportion of incoming patients that they get. So just writing that down, hospital A is safer. But since A got a higher percentage of patients in poor condition, its overall survival rate is lower than B. Moral of the story, you should always treat data like this with a grain of salt when there are multiple variables, even if you don't know about them, they may be in the background manipulating the relationship between the two variables that you're looking at on the surface. Again, that's Simpson's paradox. And that finishes the first topic. Let's go on now to talk about correlation versus causation, or cause and effect. I'm going to do 3 examples here. In each case, there are going to be 2 categorical variables. And the first example, there's a measure of exposure to cigarette smoke. So how many packs of cigarettes do you smoke per day, or how many years have you smoked, or something like that. And then some sort of incidence rate of lung cancer. The directions are to these, first of all, these, and both of these are quantitative variables. So the directions are, in the first, decide if the correlation between the variables is positive or negative. So all the real life experience in the world that we have indicates that relationship between smoking and lung cancer would be a positive relationship, or greater than 0. Now, the rest of the directions say use dash double arrows for association. Okay, so there's a relationship between these 2 variables. Certainly, it's r greater than 0, as we noted. And then use a solid single arrow for a linkage which is likely causal. Well, although this has not been proven, strictly speaking, in humans, it has in laboratory animals. We know that smoke is a carcinogen, and so we're almost certainly justified in saying that smoke exposure causes lung cancer risk. A large pool of animal experiments. And well, let's just stop there. Show smoke causes cancer. Also, we have a lot of incidental observations in humans to suggest the same thing. So those 2 things together make us believe this is a causal relationship. Next example, geographic density of crimes and geographic density of churches in a county. Let's say Grant County. And so what I mean here is Grant County has a fairly regular structure of roads like this. And there are individual blocks, and I'm saying, let's go to each of the chunks and first of all, go back maybe 10 years and count how many crimes were recorded as being committed in that particular square mile, or whatever size section we're taking. Okay, maybe 2. And maybe in the next block, 0, and the next chunk, 0, and the next one, 3, and so on. And then similarly, we're going to go to that same geographic area and count the number of churches in that area. Okay, so maybe 1, and then 2, and then 0, and then 2, and so on. This is paired quantitative data. And I ask, first of all, is the association between these 2 positive or negative? So one train of thought might be, well, churches hopefully have good influences on people. Hopefully Christians commit crimes at a lower rate than other people, and therefore the higher the number of churches, the lower the crime density, and R would be negative. In fact, lots of data shows that R is positive. In fact, the correlation is pretty strong positive. So then an interpretation would be, oh, okay, well, if churches go with crime, then to solve our nation's crime problem, what we should do is go out and burn down the number of churches, as many as we can. That doesn't seem quite right either. So suggestion that maybe something else is going on. You think about it a little bit. Who commits crimes? People. So were there going to be a lot of crimes committed? Were there a lot of people? Who builds churches? People. Were there going to be a lot of churches built? Were there a lot of people? And so out in the country, both the crime rate and the church density are low, whereas maybe in the center of Marion, the crime is higher and the number of churches is higher, leading to positive correlation. Well, what's going on here is we have a lurking variable. It's population. And probably, I suspect, the causal effect between crime density and church density is rather low. What really is non-negligible in this situation are the causal relationships. Population causes churches to be built. Population causes crimes to be committed. And then because the same lurking variable is causing both of these to change in the same direction, the correlation between the two ends up being positive. So the correlation is incidental. Results from the causal relationship of the lurking variable population. And so the potential here for misunderstanding is huge, right? If we neglect or don't think of this lurking variable, we can come to all sorts of conclusions that churches cause crime or crime causes churches or whatever, when in fact that's not at all the case. Other examples might be diet and health. So if you eat a lot of broccoli, you'll probably tend to live longer. That may be the broccoli helping you, but it's also a fact that people who tend to eat a lot of vegetables probably also don't smoke and maybe get more exercise than their counterparts. And all of those are lurking variables, making a very complicated situation. Let's look at a third and final example. The number of years of education a person has and his or his income over lifetime, so total earnings over your lifespan. It's not controversial, I think, to note that the correlation between these two variables is also positive. Higher education levels are associated with higher income levels. And there's almost a certain causal effect going on here. If you have more education, you have access to jobs that pay more. But that's not the whole story. If you think about it a little bit, if you're responsible for paying for your own education rather than your parents, the more money you have, the more access to education you have. So maybe to some extent, there's also a causal relationship going this way. But maybe more important than what I just mentioned is the fact that family background and demographics have something to do with this as well. So parents, income, and whoops. What's going on there? Well, parents' income is certainly related to their son or daughter's education level, and probably in a causal sort of way. Parents pay tuition. Parents' income may also be related, causing, in fact, your lifetime income through things like establishment of a work ethic, reliability, perhaps genetic background for manual labor jobs. Are you strong and healthy and able to do those jobs, and so on. And so We call this effect confounding. We could also put like parents' education level here as another lurking variable. The relationship between education level of a person and his or her lifetime income is confounded by a lot of these background variables. And so what causes what, or what is most important in causing what, is really hard to establish in a situation like this. Finally, here are just a few things for you to think about. I used to think correlation implied causation, then I took a stats class, now I don't. Sounds like the class helped. And here's a great answer. Well, maybe. It's the best answer you could give in a situation like this. Or here, another huge study found no evidence that cell phones cause cancer. What was the WHO, World Health Organization, thinking? I think they just got it backward. Ah, well, take a look. Graph. Cancer incidence going up in the 70s and 80s. Cell phone usage starting in the 90s. There are so many problems with that. Just to be safe, until I see more data, I'm going to assume cancer causes cell phones. So take your pick. And we will stop there. Thanks.